Welcome back to Calculus 2. I'm Dr. Jeff Groh. Today we're going to talk about infinite series. We mentioned in our last lecture that a sequence is a list, but a series is a sum. These are intuitive notions. If it comes to an infinite sum, what do we mean by that? Let's look at a following example. What if I have 1/2 plus 1/4 plus 1/8 and so on forever? We may express this as the sum, as k goes from 1 to infinity, of 1/2 to the k, but still, how do you add an infinite number of numbers in finite time? And how can you possibly get a finite result? This was a problem that plagued the ancient Greeks. Zeno of Elea was a student of Parmenides, and Parmenides taught that the fundamental element of existence, at its core, is the one. And the one is changeless. So anything that is changing must then be illusion. So Zeno tried to argue in favor of Parmenides' philosophy that motion is impossible. And his basic idea was, in order to go from point A to point B, you would have to go half the way there, and then half the way again, and then half the way again, and so on ad infinitum. It would take a certain amount of time to go half the distance, and another amount of time to go half the remaining distance, and another amount of time to go half the remaining distance of that, and so on. So to go from point A to point B, you would have to add an infinite number of times together. And he thought this was so absurd. You can't add an infinite number of numbers together and get a finite result, and so he argued motion is impossible. To go from any point A to any point B would take an infinite amount of time, and therefore motion must be an illusion, consistent with the philosophy of Parmenides. Now, what Zeno didn't understand is that it is possible to get a finite result from these sums. But to construct the theory, we do need to be a little careful not to use terms like infinity too carelessly. So when we have a sum like 1/2 plus 1/4 plus 1/8 and so on, which we have agreed that we're going to write as the sum as k goes from 1 to infinity of 1/2 to the k, what are we really doing? We need to make sense of this sequence of symbols in such a way that we don't use undefined terms. So we're going to define an infinite series as follows. Let A sub k be an infinite sequence let S sub n be the sum as k goes from 1 to n of A sub k, be called the nth partial sum of the sequence. The nth partial sum is always defined, since it is merely a finite sum of real numbers, or complex numbers in the appropriate setting. A series is the sequence of nth partial sums. So the series will always exist even if the sum isn't finite. The series converges if the limit as n goes to infinity of that nth partial sum, which is, by the way, the limit as n goes to infinity of the sum as k goes from 1 to n of a sub k, the series converges if this limit exists. Otherwise, the series diverges. By the sum as k goes from 1 to infinity of a sub k, we mean the limit as n goes to infinity of the sequence of nth partial sums, which is, by the way, the limit as n goes to infinity of the sum as k goes from 1 to n of a sub k. So the infinite series, the infinite sum, is equal to the limit of the nth partial sums. The limit may not exist, in which case we say the series diverges. And if the limit does exist, then the series converges, and it converges to that sum. Let's go back to the problem of Zeno of Elea. The first partial sum is 1/2. The second partial sum is 1/2 plus 1/4, and that is 3/4. The third partial sum is 1/2 plus 1/4 plus 1/8. If this adds up to 3/4 or 6/8, we add one more eighth, we get 7/8. And you can easily check that the fourth partial sum is 15/16. Can you give me a formula for the nth partial sum? If you check this out, the denominators are all powers of 2. 2 to the n. The numerators are all 1 less. We can rewrite this as 1 minus 1 over 2 to the n. If you calculate the limit as n goes to infinity, the second term goes to 0, so the whole thing goes to 1. So if you add 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 and so on, you end up with 1. So what is it that Zeno got wrong? Zeno didn't understand convergent infinite series. Of course, that was a concept that would take a long time to find out and develop. So let's look at some more examples. What if I have the sum as k goes from 1 to infinity of 1? This is going to be, when k is equal to 1, 1. When k is equal to 2, I add 1 and 1 and so on. You can see that the first partial sum is 1. The second partial sum is 1 plus 1, which is 2. The third partial sum is obviously 3. And the nth partial sum is n. You can see then that the limit as n goes to infinity of the nth partial sum is positive infinity. So this series diverges to plus infinity. Just as you might anticipate. Let's look at a series that is of a very special type. This turns out to be something called a telescoping sum. I'll explain why it's called that in a moment, but first I want you to note that the terms of the sum are kind of a rational function, and we can perform a partial fraction decomposition on this sum. If you multiply both sides by the denominator on the left and on the right, on the left the denominators just cancel. On the right we distribute to both terms and we end up with a times the quantity k plus 1 plus b times k. If you set k equal to 0, that implies then that a is 1. If you set k equals negative 1, then you get 1 equals minus b, or b equals minus 1. We may express the sum then as the sum, as k goes from 1 to infinity, of 1 over k minus 1 over k plus 1. Now I want you to think about the partial sums. The first partial sum is 1 minus a half. The second partial sum is 1 minus a half plus, when k is equal to 2, 1 half minus 1/3. You get these canceling. What is the third partial sum? We'll have 1 minus a half plus a half minus a third plus, and when k is equal to 3, a third minus a fourth. We can see that we get a bunch of cancellations here. Can you tell me what the nth partial sum will be? Notice this number is always 1 more than what you have as a subscript on the partial sum. You get 1 minus 1 over n plus 1. It follows then that the limit as n goes to infinity of the nth partial sum is 1. And so this series converges to a sum of 1. The idea of telescoping is like this. You have the old pirate's telescope, which has a bunch of different segments. These things can collapse to form a compact unit, and that's what's going on with these cancellations of these terms. The sum is collapsing down to just the first and the last term in the entire sum. We're next going to look at geometric series. Remember, these look like a plus a times r plus a times r squared plus a times r cubed, and we would like for these to go on forever. We can express this in sigma notation as the sum, as k goes from 0 to infinity, a times r to the power of k. We would like to know when a geometric series converges and when it diverges. And so to answer these questions, we need to calculate the nth partial sum. The nth partial sum of a geometric series is A. Let's say that we stop at n, but we're still starting at 0. A times r plus all the way out to a times r to the power n. Now there's a special trick, and you might want to remember this. Let's multiply through by r. If we put an extra factor of r onto every single term, we get a sum that is almost the same. So what we'll do is we'll subtract these two sums. And when we do, almost everything will cancel down the line. The only things that won't are the last term in the r times s sub n and the first term in the s sub n. We'll have a r to the n plus 1 minus a. We'll factor both sides. On the left-hand side, we'll factor out the nth partial sum. On the right-hand side, we'll factor out the first term. We have then a closed formula for the nth partial sum. It's the first term times r to the n plus 1 minus 1 over r minus 1. This formula for the nth partial sum of a geometric series might be the most important formula affecting your life. It is exactly this formula that is used for calculating amortization schedules on loans. So anytime you buy a car or buy a house and take a loan out, to do that, they're going to use this formula to figure out how much you're going to have to pay. We are going to be primarily interested in the limits of these partial sums. Now, we have this exponential function. If r is equal to something like 2, this is going to blow up and go to infinity. But if r is something like 1/2, it'll go to 0 as n goes to infinity. So whether or not you get a finite sum or a divergent infinite sum will depend upon whether or not r is big in magnitude or small. You can see that in the limit, as n goes to infinity of the nth partial sums, you will get a finite sum. If this goes to 0, we'll push the negative through the denominator and end up with a over 1 minus r. But that's only valid if the magnitude of r in absolute value is less than 1. It diverges otherwise. We have a special notation. The infinite sum of a geometric series, if it converges, is the first term divided by 1 minus the common ratio. This is a formula I want you to remember. Let's apply this to the problem given by Zeno of Elea. This is a sum as k going on forever, as k goes from 1 to infinity, of 1 over 2 to the power k. In this case, the common ratio is 1/2. That is the value that gets raised to higher and higher powers. And the first term of the sum is 1/2. So this infinite sum will be the first term divided by 1 minus the common ratio. 1 minus 1/2 is 1/2. A number divided by itself is 1, giving us the same value that we found earlier. As you can see, the more you know, the easier this gets. As another example, suppose I have the sum. We can start this anywhere. 3 to infinity, Suppose I have 4 times 2/3 to the power k. You can see that the common ratio is 2/3, which has a magnitude less than 1, and therefore this will converge. What does it converge to? It converges to the first term. The first term is 4 times 2/3 to the power 3, and then over 1 minus the common ratio. 3 cubed is 8, times 4 is 32, 3 cubed is 27, and we're dividing by 1/3. When you divide by a fraction, you invert and multiply. So the sum will be 32/9. As another example, consider the fraction 0.123, and repetans. This repeats over and over again. We can think of this as 123 over 1,000 plus 123 over another 1,000, so 1,000 squared, plus 123 over 1,000 cubed, and so on. We can express this as the sum, as k goes from 1 to infinity, of 123 times 1 over 1,000 to the power k. We can identify this immediately as a geometric series. The common ratio is less than 1 since r is 1 over 1,000. It follows then that this series converges, and it converges to the first term divided by 1 minus the common ratio. This gives us 123 over 1,000 over 999 over 1,000. When you invert and multiply, the 1,000s cancel, and the sum is 123 over 999, which we may further reduce, but the point being, we've converted this repeating decimal into a fraction. As you can see then, this procedure can be generalized to all repeating decimals. So all repeating decimals may be expressed as a fraction. Before proceeding on, I'd like to codify something that we've discussed as a theorem called the geometric series test. And it goes like this. A geometric series, which we'll express as the sum as k goes from 0 to infinity of a times r to the k, converges to a over 1 minus r if the magnitude of the common ratio is less than 1, and diverges if the magnitude of the common ratio is greater than or equal to 1. Next, we're going to talk about something called the nth term test for divergence, also known as the divergence test. The statement is fairly simple. If you take the limit as, say, k goes to infinity of a sub k and do not get 0, then the infinite series involving this sequence a sub k must diverge. We are going to prove this, but first we need to discuss a little bit of logic. The logical structure of the divergence test is as follows. If the limit as k goes to infinity of a sub k is not 0, then the series diverges. You cannot possibly get a finite sum if the terms don't go to 0. This is in the form of statement A implies statement B. Suppose statement A is I am in Paris. And for the sake of argument, let's suppose that we're in Paris, France, not Paris, Texas. And let's let statement B be I am in France. So if you are in Paris, France, then you are in France. Let's suppose that this is a true theorem. The converse is with the assertions the other way around. If I am in France, then I am in Paris. That's not a true theorem. So just because a theorem is true does not mean that the converse is true. In this case, the converse is false. However, there is something called the contrapositive. Not B implies not A. If I am not in France, then I am not in Paris. It turns out we can prove that a theorem is always logically equivalent to its contrapositive. So if one is true, then the other one must also be true, and vice versa. For sake of completeness, we should put in the inverse as well. Not A implies not B. If I am not in Paris, then I am not in France. That too is not a true theorem in this case. Let me point out that the converse and the inverse are also logically equivalent. After all, they are contrapositives of each other. Let me point out the contrapositive. If the series does not diverge, well, if it doesn't diverge, it must converge. Then, if the terms don't not go to 0, canceling out that double negative, we have the terms must actually go to 0. It's this form that we are going to prove. We're going to prove the contrapositive of the divergence test, though the divergence test will always be used in this form. We'll see if the terms don't go to 0. If they don't go to 0, we may conclude that the series diverges. In the divergence test, the conclusion will never be the series converges. It will always be the series diverges. Never use the divergence test to try to prove convergence. And the reason is that the converse of this statement is false. The converse of the contrapositive is called the inverse. The inverse says that if the terms go to 0, then the series converges. That's untrue, and we will prove it. We will prove it by counterexample. To prove something is not true, all you have to do is exhibit one example where the statement fails. We will show a series that has terms that go to zero, and yet nonetheless the series diverges. But we'll do that after we prove this version of the divergence test. So keep in mind what it is that we're trying to prove. We're trying to show that if the series converges, then the terms must in fact go to zero. Here's what we're going to do. Set S to be the limit as n goes to infinity of those nth partial sums. We know that nth partial sums must have a finite limit because the series is assumed to converge. Also, note that Sn, the nth partial sum, is the n minus first partial sum plus the nth term. Now, we know that the nth partial sums converge to S. And we also can see that the n minus first partial sums must also converge to S just one term later. They will arrive at the same limit, which implies that A sub n is the nth partial sum minus the n minus first partial sum. This sequence converges. This sequence also converges, which means that an is the difference of two convergent sequences. If you have a sequence that is the difference of two convergent sequences, then that sequence converges. But what does it converge to? We need to prove that it converges to zero. That's easy. We'll just take the limit as n goes to infinity of an, and we'll get the difference of these two limits. This one tends to S, this one also tends to S, and so we get zero, and the proof is over. We deduce then that if the series converges, then the terms must go to zero. But we also get the contrapositive of that statement. If the terms don't go to zero, then the series doesn't converge, it diverges. As an example, suppose we have the series 2 to the k. We know in the limit as k goes to infinity of 2 to the k, we get plus infinity and not zero. Since the terms didn't go to zero, the series diverges by the divergence test. This demonstration illustrates three parts of something that I want you to do with every series that I give you. First, I want you to tell me what test you're using. Second, I want to see evidence that the test was actually implemented and the condition for the test is employed. Third, I want the conclusion of the test. Give me those three things on each series that you are confronted with, and the next exam will have a large number of series for you to analyze. As another example, consider the sum as k goes from 1 to infinity of 1 plus 1 over k to the power of k. You might remember that the limit as k goes to infinity of 1 plus 1 over k to the k is equal to e. We proved this in the last lecture using the e to the log mechanism. Since this is not zero, the series diverges by the divergence test. Let's look at one more example. The bouncing ball. Let's suppose that we have a super bouncy ball that we drop from a height of 7 feet. And that when the ball hits the ground, it bounces back up, but it doesn't go all the way back up. Let's suppose it goes to only 7 times 4/5 feet back up. It only goes 80% of the way back up. And then it goes down that amount again. When it goes back up, it goes back up 80% of the 80%. So we have to put another factor of 4/5 on to the previous height. And that's going to go down that same amount and then back up 7 times 4/5 cubed. And so on. How far does the ball go by the time that it stops? What is the total distance traveled by the ball? Well, you can see that it goes down 7 feet. But it goes back up and back down 7 times 4/5. That's going to be 14 times 4/5 because we have to double it. It goes up and down. Plus 14 times 4/5 squared, and so on. Can you see what's going on? If this number were 14 instead of 7, we would have exactly a geometric series with a common ratio of 4/5. It converges by the geometric series test, but we don't have 14, we have 7. So what can we do? Well, how about this? We'll make it 14, but we'll subtract 7 to balance that out. So the infinite sum will be this -7 plus the sum of the remainder, which is a geometric series. The first term is 14, and the common ratio is 4/5. So we have this -7 plus 14 over 1/5. Remember, you invert and multiply when dividing by a fraction. 50 and 20 makes 70, so the total distance traveled is 63 feet. Isn't that remarkable? After an infinite number of bounces, the ball has gone a finite distance. Another subsidiary question is, how long does it take for the ball to make this infinite number of bounces? How long a time does it take for the ball to bounce an infinite number of times? Is that finite, or is it infinite? For an object to drop a certain height, the amount of time that's elapsed involves the formula h equals h naught. If we're letting it go with free fall, it's 1/2 g t squared, where g is the constant acceleration due to gravity. You remember who figured out that g was constant? That was Galileo. If h naught in this case is 7 feet, the distance it falls is down to a height of 0. It's going to go to all of those 7 feet. G in this case is 32 feet per second squared. So we're going to get the equation 16t squared is equal to 7. We'll divide by 16 so that the amount of time, which we'll assume is positive and not negative, will be the positive square root of 7 divided by 4. That's how long it took to drop the initial 7 feet. The next time around, though, it's going both up and down. It will take just as long to go up as down, but it's only going to go 4/5 of this 7. So on the next step, we're going to have 16t squared equals 7 times 4/5. We'll divide and get t squared equals 7 times 4/5 times 1/16. T squared is going to be 7 over 20. Taking the square root, the amount of time is the square root of 7 over 2 times the square root of 5. But remember, we have to double that time. So our running total is root 7 over 4. If we double this time up and down, it's going to be the square root of 7/5. How long does it take on the next cycle, up and down? On the next cycle, up and down, we're going to have 16t squared equals 7 times 4/5 squared. We'll divide the 16 off and then take a square root. We'll have the square root of 7. The square root of 4/5 squared is 4/5, and it's times 1/4. So we get root 7 over 5. And don't forget, we have to double that time. On the next bounce, it's 16t squared equals 7 times 4/5 cubed. We'll divide the 16 off and take a square root. We'll get a root 7. When we take the square root of 16, we'll have 4, and over here we'll have 4/5 times the square root of 4/5. You can see that the 4's cancel and we multiply by 2. And so we'll have 2 times the square root of 7 over 5 times the square root of 4/5, and so on. This is going to be, except for this first term, geometric. What is the common ratio? If you take 2 root 7 over 5 and multiply by the reciprocal of the previous term, you'll get 2 divided by the square root of 5. Similarly, if you take the square root of 4 is 2, that gives us a 4 out front. If you take 4 root 7 over 5 root 5 and multiply by the reciprocal of the preceding term, the root 7's go, the 5's go, but 2 cancels, and you get 2 over the square root of 5. We deduce that the common ratio is 2 over the square root of 5. We see then that the sum, the total time, is going to be root 7/4. This term is just going to come along for the ride, plus the first term, root 7/5, divided by 1 minus the common ratio. Let's simplify that. We'll simplify first by multiplying top and bottom by root 5. We'll have root 5 minus 2. We could simplify this more, but the point was to find the amount of time. We see that the time is definitely finite. And what is more, we can use our calculators to find a decimal approximation. My calculator is giving me about 11.869 seconds, or about 12 seconds. In a total of 12 seconds, the ball will have made an infinite number of bounces and traveled a total of 63 feet.